continue from where we were. So, this is where we're starting. Yeah. Okay, so we're looking at functions, maps, inverse images, and yeah, so the first time you have to evaluate this function called show URL. It'll go and fetch the URL and show it for you. So you have to evaluate it at least once per notebook. It's not a built-in function. Okay, so here's a slightly more mathematical notation for function. So we have f of x, or a function f. One way of writing it is it goes from x, baby x, to y. Or you can also say, the function x. So the function f goes from x to y. So these are all equivalent notations. So you'll see in all these books. So this is the same. Yeah. So we can now start defining functions using the sets we're familiar with, the natural numbers to integers. So we can say f is a function from the set of natural numbers to the set of integers. That's what this means. The other way to say is that f, so you'd say f is a y-valued map. It's a y-valued function of an n-valued variable. Y-valued function of n is your natural numbers, n-valued variable. So as you see, where we're going is y can be some arbitrary set, right? It can be road segments on the OpenStreetMap, if you want. Okay, and then this thing I like a lot. This is so-called Bourbaki notation. So you can write x maps to some value f of x or y. So this has got a little thing like this. So this is called maps to. So this is nice because now you can talk about every little x in x maps to some some f of x. Okay, so I think Bourbaki. You guys know about Bourbaki? Bourbaki. Okay, you know about it, but so Bourbaki. So is that the guy's name they may use? Yeah, so it's a group of mathematicians. They call themselves Nicolas Bourbaki. And then they basically got together and wrote basically condensed a lot of 20th century mathematics and to come up with unified notation and so on. So this was a huge project. So this is the Bourbaki group, and so a lot of the notation we have is so theory of ensembles. Okay, anyway, so that's where this all comes from. Okay, so what we will be seeing, hopefully before the end of today, is so these are now n-valued variables, right? That means these variables, sorry, in this I'm doing specifically x and y, x-valued variables. So we want these x-valued variables to not be deterministic variables, like right now. It's deterministic because for every specific fixed x, I get a specific fixed y, but I would like to be able to, we would like to be able to generalize that when this guy itself is going to be a realization of some random object, okay? So we will look at x-valued random variables soon. Okay, so that's about functional notation. Yeah, so I'm just parsing the Wikipedia page there. So now encoding a function or map as a set of ordered pairs is our next stop. So here we're using Python dictionaries in sort of a black box way. So this essentially is the notation for initializing a Python dictionary, creating one. So you put these curly braces, which are in maths used for set notation, but here for Python dictionaries, they're used the same way. So I can have my key and value as a pair separated by a colon, and then I can put comma in my second key value pair, and my third key value pair, my fourth key value pair. So this is the fathers-daughters map. So I can represent them as these specific ordered pairs in a dictionary. So we can find the type. It says type is a dictionary. So this is a Python or built-in data type dictionary. So yeah, we will see more about dictionaries soon. So the nice thing about this is I can say find father's map of Anu, which is now my key. So when I give it my value in the domain or the key, it gives me the value Ras, right? Just looks it up and returns it. So this is just the same. I can just do a pretty print. Print the father of Anu is. Now this is find daughter's map, right? So this is the inverse image of find father's map. But remember, my arguments are just Jonathan and Raz, okay? And if I really want, I can put in, was it Fred, the guy without any daughters? Was it Fred? So I can put an empty list here. I think that'll work. Fred has no daughters, right? So if I want, I can encode it. I mean, formally, that's what will happen. If I ask what's the find daughter's map of Fred, it'll be nothing. So I'm simply walking through the dictionary using these for loops, which we'll see soon, and printing. So here's using a numerical function. So I can do my function map, is it's mapping -2 to 6, -1 to 3, and 0 to 2, and 1 to 3 using this function. Y of x is x squared plus 2. Yeah, this is again another notation. So you can also write, you can also have a function that you can just ask what is y of x directly. Okay, so once I've sort of hand computed it, and then I can code it as a dictionary. So then once again, I can ask what is my function map of -2, and then if I ask what is my function map of -20, I get a key error because -20 is not one of my keys, right? It's not one of these values I say, -2, -1, 0, or 2. So that's just Python dictionary saying, oh, it's not one of the things you've told me about. Okay, so that'll work. Okay, the next example is encoding functions as a procedure. So this is the other way, because the dictionary way is hard coding it, right? That you can only do for a small enough set of cases. So here, the idea is that here are the basic steps of defining a function. So here I use this keyword def to define function. And then I put the name of the function, which is my func. So it's almost like Scala. And then you open parentheses and close parentheses, and inside the parentheses you put the argument for the function, right? And then you need this keyword or key character colon. So that'll be telling you that you're starting the definition. And then here is the doc string or the help string in triple quotes. So you can say something. It's a function to return x squared plus 2. And then because it's such a small function, there's just one line in the body. You can just say return x squared plus 2. Okay. So unlike Scala, you have to explicitly say return in Python. Okay, so let's evaluate that. So that's basically all these steps here are these 6 steps. So you can ask, what is my func question mark? So now it's giving me my doc string. It's a function of to return x squared plus 2. So then, of course, you can now give it arbitrary arguments, right? Well, for which those operations are defined, x squared plus 2. So 0.1, remember this is MPFR reals. So it'll go in and give you 2.01. So also remember, if you want to use Python types, so you just put in float, and this should give you 2.01. This is Python's float now, right? So, yeah.
And the evaluation,
yeah,
the function is done in such a way that I can compose function. If I don't have another function, let's call it D, that makes the
you can call a function. Yeah, you can pass. Yeah. So if you have another function defined, you can pass it as an argument to this function.
Because you told us that Scala is a functional language?
Yeah, so in Scala, yeah, functions are first-class citizens, but you can do functional programming in Python as well. But we'll get there. So there are things called Lambda Expressions and things like this. But for now, let's just make sure we understand like what happens when you pass in different types and inheritance of operations for input arguments being, so for example, let me put, what was it, 0.1. So let me do 1 over 10, right? So this is Sage rationals, right? It gets evaluated. So I think I have something downstairs. So let's just follow the recipe for a minute. So this is now, yeah, so if you just type in this, you're going to get some indentation error, because so in Python you do the blocks, you align the blocks in a straight line like this. 1, 2, 3, 4. There's 4 white spaces. This is a standard. I think you can just use 1 white space will also work, I think. It works, right? I mean, I think it's, yeah, I think 4 is the standard. Let's do that. Because the tab is typically 4 white spaces. So you just have to control the indentation blocks. So that's a standard Python thing. Okay, now let's just plot. Let's use this black box function plot magically. So I'm saying plot my func of x, but x goes from -20 to 20. So this will be what? It's a quadratic shifted by 2, right? So that looks, oh my gosh, it's huge. Okay, so it's hard to see, but it's sitting at 2, not at 0. So then if you do question mark plot, you get a lot of options, So, okay, I'm not going to read all of it now, but I think one of the main options that I like is the fixed size one. So you can control the fixed size to be 6 by 3. So then you can kind of see it a bit nicer within the browser window. So So, but you know, there's a lot that's being sort of obscured by this plot, right? Because the function looks nice and continuous, right? It's like a smooth line, and but if you really zoom in, you're going to start seeing a polyline, you know, just like the OpenStreetMap, a whole bunch of lines connected by dots. So to better understand it, let's play with this interact. So what we're saying is that the value for x is 11. So 3, 11 is our usual ordered pair representation of this function, right? So in the Bourbaki notation, 3 maps to 11 and 4 maps to 18 and so on. So you can kind of play around with this. So the idea is that this function is encoding all of these ordered pairs, but it's doing them in this sort of procedural way. So every time you give an input, it'll give you some output, right? And what about this blue line, really? So if you look a little bit under the plot's hood, so here's a few more things I can throw in at it. So I can say plot points equals 5. That means just throw 5 points at it, okay? So I'm only interested in making a plot with 5 points. And then I say my marker style is just point, okay? So it doesn't connect the lines. And my line style is empty, so it doesn't connect anything. And then I'm saying randomize equals true, which means it somehow randomly draws these 5 points to plot from my range. And yeah, these are some other parameters. Let's ignore those for now. So if I evaluate this, I'm going to just see 5 points, right? So that's what's really happening in the plot. And then if I say line style is dash, it's going to connect these 5 randomly plotted points, right? And then if I say my plot points is 100 and line style is 1, now I'm starting to see something that looks smooth, right? This is basically what is happening when you, and then if you ignore the marker and just, this is close to what you saw, right? Okay. And because I'm only plotting from -2 to 2, I can actually see this gap a little more easily. So yeah, what you're actually visualizing in a plot is usually a polyline. And I guess, why is this important? So, you know, you can have a function that has a very, very tiny spike here. You know, it can be a very, very small spike, so that if you, even with 100 points or 1,000 points, you may never drop one of these random points in that spike. So then, you know, when you plot it, you will not even see the spike, right? But the spike is already encoded in the function's expression in the body. So once again, this is not rigorous numerics, so yeah, you won't really see some things. So the way I will try and develop plotting down the road is I'm going to start just letting you guys play directly with geometry primitives. So we will kind of avoid like GUI things for a while. So I'll let you compose a dot with a circle closed or filled up and put dotted lines. So you'll actually start playing around with geometry primitives when you plot things, just initially. Okay, here is another function. This is a quadratic function of x with 3 additional parameters a, b, c. Okay, so this is ax squared plus bx plus c. This is a so you should kind of have an idea of what this is encoding. So we've found, right, so we have f of x, or my quad is now a x squared plus bx plus c. So if a is 0, I just have bx plus c, right? That's just the equation of a line, the intercept and the slope, right? So now I just have this extra term. If this is not 0, then I have a quadratic term, right? So the primitives for this is basically, what are you playing with? You're playing with, so here's the real line, right? So this is where my arguments live. So this is a real valued function with real valued arguments. So this thing here, C is basically playing with 1. So if I multiply this constant 1 by c, it goes up or down. Okay. Okay, that's the, so this is actually the polynomial x to the 0, right? And then b times x is basically, what is x equals x? So this is our x, and this is f of x, right? So we're composing each piece. So when x is equal to x, I have this line, right? This is the x line. So when I do b times x, what is b times x going to do? B is 1. 1 times x is just, again, this. You understand? I'm just encoding the variable geometrically. Yeah. So if I increase b, it'll go like this. If I decrease b, it'll. I mean, if it's negative, if I decrease it, it'll go like this. And then if it's 0, it'll be hugging here, and then so on. And that's the same. Now x squared is also going to be sitting here, right? It'll be quadratic, something like this, and so on, right? And x cubed is this. So a polynomial is simply linear combinations, you know, scalar multiplications of each piece added together, right? That's pretty rich class. So that's what we're going to do now. So we pass in 4 arguments, a, b, c, and x to this, my quadratic func, right? And so I can now specify to be like this. Then I'll get, you know, specific value. Oh, wow, why am I not getting anything?
You have to uncomment.
Oh,
Return.
I thought
About
oh.
in the function.
Oh yeah, good. Is that my instructions? Okay,
Yeah.
that's good. Thanks. Yeah. Good. Okay. 1, 0, 2, 10, whatever, right? So you can play around, and so all of those 4 things are being controlled. And generally, we think of this as being our argument, right? So if that's an arbitrary x, then this quadratic function will behave in some way. So here is a simple one with a0, b0, and c2. So yeah, so we are killing the linear part and just giving you what we had before. So if I kill the quadratic part, this will be boring, right? This will just be the constant 2. So anyway, if I kill this to be -1, so that'll be my negative sloped thing moved to 2, moved up by 2. So okay. So this sort of sets us up for understanding sort of polymorphism and types and type errors in Python. So we can call the same function myfunc with different types, and the operations in the body of the function, such as power and addition, will automatically be evaluated. We already saw that for rationals, right? So, and then integers as well. And we can put in Python ints by calling int of 2. Now something interesting happens, right? What if I do myfunc of hello? So myfunc of hello, so I'm passing in a string, right? So if you read the type error, it says calling myfunc on an input string argument results in a type error. And if we dig slightly deeper, can we see anything? It's saying this binary operation exception is happening for raising. You know, raising is the power symbol, I think. Right? And then unsupported operand parents for plus. So it's trying to add something of type string to something of type integer ring, right? Because it's the power of 2 part, right? Remember this one. So to fix this, yeah, so it's here's the function, right? X squared. So it doesn't like the string raised to the integer ring's power of 2. Okay, so yeah.
I think it doesn't like adding 2 to the string, not to the power.
Yeah, so yeah, power should work. Yeah, that's what I say here. Yeah, power should work. And oh yeah, it doesn't like adding 2 to it. So why did the error unsupported up? Oh yeah, unsupported operands type plus. So this is the real error, right? Why was I looking at course model? Sorry, I thought I saw something. Okay. This causes so much headache. What? Okay, so this is coming from. Okay. All right. So anyway, so this is the real error, right? The addition operator is not defined. So as we see, if you take a string and parse it just repeats it many times, right? High times to the power of 3 is high, high, high. But this is fine, right? If I can take 2 strings and concatenate them, but I cannot take a string and add it to 2. That was the problem. So then what we can do is do like this.
Just a quick one. When I run the first one, hello raised to 2, I get a warning saying that this is deprecated and will.
Oh, okay. You're on you're the same version as me, right?
So I get this. Then I do this, and it's okay.
Oh yeah.
So it's just 1v1 once.
Okay, you're already on stage 8.2.
Yes.
Because I'm on 8.1. That's interesting. So what do they say will happen?
It says it's going to be deprecated.
Yeah.
What if we multiply the string?
Yeah,
No, multiply.
It works raising it to
Yeah.
the warning.
Yeah. So those who are on 8.2 will get a warning and then it'll work. I mean, I should have redone everything for 8.2, but 8.2 just got released 4 days ago. I'm not going to change notes for every 4 days. But it doesn't matter, right? That's something you guys, it's good that we have different versions actually. Okay, so look what I've done now. I've just taken x, whatever comes in, I raise it to power 2 and then add whatever came into it, right? So this should work, right? This should work for both cases. Well, it's a different meaning function, but that's okay. So if I do high, it'll give high, high, and then high. Okay, that is something people in Python love this or whatever. I find it very nervous because, whatever. You can put something in, something will come out, but doesn't mean that's what you want. But this is nice, right? Because this is parametric polymorphism, right? But you have to be cautious. So now we get into mathematical functions. So these are standard ones. Cosine of 0 is 1, right? So let's see, how many of you remember trigonometry? So, remember this? So this is 0, 0. So this is a circle, radius 1, right? So then what is the basic idea in trigonometry? So this is some angle theta, right? And if it's here at 0, it's defined to be 0, 90, 180, 270, and 360, right? Going this way. And then what is the definition of cosine theta? So this is the adjacent side, right? So it's called the adjacent side, and what is this? The opposite side. And this is called the hypotenuse, right? And this is constructed to have a 90 degrees, right? So cosine theta is what? Adjacent side divided by hypotenuse, right? So do you agree when theta is 0, cosine theta is adjacent side, which is radius 1, divided by hypotenuse, which is also 1. So it should be 1 over 1, which is 1. So sine theta is what? Opposite side by hypotenuse, right? And sine 0, well, once again, this triangle is just hugging this line. It's just Fine. So that's 0 now. 0 divided by 1 is 0. Okay, and sine pi. So when it's this way, right? This will be pi, beta will be pi, and so on. So now what is the opposite side? Okay. So anyway, I'll just black box some things. It's technical already. Is it that side or is it this side? Okay, so so basically pretty much all the math functions are just like any other high level thing, right? So you can call them, so here's cosine of half, and then cosine of half to some digits of precision. And then we can also pass in Python float cosine of half. So maybe this is not what you want. Maybe you really want cosine of float of 1 over 2. Okay, so it depends on what you want. Okay, exp, pi, you can use all of them. Log is natural log, base e. Okay, so x to be minus 2. So if you assign x to be minus 2, and then we can use our usual method and find quite a lot of things. Find on integers. So for example, I can do x dot absolute value, or I can also write absolute value of x. Okay, and I can just ask for some help, or type help of abs as well for more details. So now let's get into collections in Sage. So now we're sort of looking at lists in a bit more detail. So list is a built-in sequence type. So here are all the built-in sequence types. So we've already seen str, string, and Unicode. These are built-in sequence types. So our lists, tuples, byte arrays, buffers, and X range. So okay. So this is how we define an empty list. L1 equals just 2 square brackets, so it's an empty list. And then we can display L1. So here's a list of 3 strings as fruit, and then we can append. So appending is a nice operation on lists, so we can keep appending things to the list. And here is a list of integers. And then you can ask what's the type of list. So it'll just tell us it's of type list. So here are various useful functions that we can use on lists. So length is a very common one. So if you do len, it'll give us the length of the list. Then this is how you will access elements in the list. So if I do square brackets of 0, it'll give you the first element in the list, and it's indexed by 0, starting from 0. So, so L3 of 3 is going to give me the 4th element in the list. Okay. So L3 of 4 is going to give you an index error because the list index is out of range. This is a very common error you want to not worry about and fix it.
You can also list -1 to get the last.
Yeah, I think we do that downstairs. Yeah, I think so. Yeah. So he's saying you can do -1. Yeah, so I believe we do something like this. Yeah. So this just gives you the last element. Okay. Yeah, and also if I do -3, -3 gives me 11. This will give me, so what's going on? I don't know. Okay, now I go out of range again. So this is just going in the other direction. Okay, so, all right. So this is again very useful. We want to grab elements in position 0 to L in the list. Sorry, to 2. So then we just put a colon. So this is called slicing. And then if you don't put any arguments and just simply put the colon, this will simply give you the whole list. So this is a slick way to make copies of the list. Right? So if you want a list called L4, which is just a copy of the list L3, then you would just do something like this.
We are that when you do the 0 column 2,
Yeah.
you obtain the element 0, but not the element 2.
No, you obtain from 0 to 1. So it's
Yes, it includes the left side, but not the right side.
yeah, because that's up to, right? So this will give you the first 3, 0, 1, 2. That's convention. So less than operation.
Less than.
Yeah, so it's like C, I don't know. Yeah, so that's that. And then, here's a very useful thing called range. It's a built-in function. So range 10 will give you all the numbers from 0 to 9. So it's a quick way to loop, create numbers starting from 0. So here is another one. So I'm starting from 100, ending, before 150, or, the last element in the range is 150, but I'm going in increments of 5. So, so that's what you get. So you can just hop, right? It's just getting used to syntaxes and inequalities and hops. So now, yeah, you can find out more about how range syntax works. So you have start, stop, and optionally steps. If you don't provide steps, it takes the step to be 1 by default. And the same with append. We can append elements to the list, so you can look up help for it. Okay, so assign the list to a variable named myList. I don't know, just create something, not just the empty one. Make sure you can use the append method. So clearly you can have multiple copies in list because they're not sets. Okay. So I'm going to do my new list. My list. So I'm going to create a copy. Length of my new list. It's 6. It's just a copy. So now I'm going to find out what the first element of my list is. It's 1. And I'm going to do my new list of 0 to 100. Now let's disclose the original list. Nothing has changed. And if I disclose my new list, here the first element should be 100. So making copies is very useful if you want to Okay, use the range to make a list of integer numbers between 4 and 16 going up in steps of 4. Assign this list to a variable named range list. Okay. Okay. So yeah, if you do this to 16, you're not going to go there, right? So you can make this to be like this, and then we're going to keep hopping forever. So we'll just stop it. You can do a 19 and still get only what I want. Okay. So the next, is everyone happy with all of this? Just some syntactic grease. So now we're going to get into tuples. So these are different beasts. A tuple is another built-in sequence type in Python, like lists and strings. The value of tuples are enclosed by curvy parentheses like this. So my tuple 1 is 1, 2, is assigning the tuple 1, 2 to this variable. And you can ask what is the type. It's a Python tuple. So I can have my tuple 2 to be a tuple of 3 elements, 10, 11, 13. So what's important about tuples is they're immutable, so they cannot be changed, right? So this is the Latin verb mutare, or to change, right? It's not changeable. So if I try to change the argument, my tuple of 0, I mean, if I try to extract the argument, my tuple 1 of 0, I can find out what it is. That was this element 1, first element. But we cannot change it. So if we try to change it to something else, it will say tuple object does not support item assignment. So it's immutable. We can't do it, which is good. So if you want to keep things that shouldn't change, then you should use immutable types. So here are some very nice, useful things you can do with tuples. They'll sort of come in handy very soon. So you can take a list. So say XYZ and another list 1, 2, 3, and then use this function called zip. Zip will take the first element in the first list and zip it with the first element in the second list into a tuple. So it'll just give you like a zip of tuples, right? That's all zip does, which is very powerful. So so here's our third example. Do you have a question?
Can you name the items in the tuples if you want to have some sort of if they have a special meaning to you? There might be age, name, or something in the tuple. Then can you?
Okay. I think if you pass these tuples into a dictionary, I think we'll do dictionaries soon slowly. Then I think you can zip this, and I think you can use this to construct a dictionary.
Okay, but I wasn't thinking of a dictionary. I was what a tuple is by itself. Item 1 could have another name.
Oh, like a case class or something? I don't know without. Yeah, I mean, I don't. I know we can do this, for example, and then I can do a of 0 will give me the first element, which is a. Then I can ask what is the first of the first, which will give me x. I mean, I can index into it, but.
Just thought it would be convenient to sort of have named.
Yeah, I mean, you can probably create a class and give it, I mean, that's, yeah. So Scala is convenient that way, right? But I'm not like I mean, I don't know enough Python to say what's the Python answer for this. So yeah, here's sets. So now I'm basically saying L6 is the range, 100 to 150 in bumps of 5. And then I'm going to create a set with that list, right? And this is just my Python set. Okay, so we already created them, just sort of just revisiting them briefly. Now, if I ask what is the 0th element of S, it's going to give me an error because set does not support indexing, right? Because sets are. But I can do this. I can put a dot after S and hit tab and see all the things I can do to it, right? I can add. We've already seen that. I can clear it. Copy, intersection, lots of operations, right? Yeah. So now if I put a capital S, ET, remember we already said this is the stage math set, so just remember that this one's got a lot more mathematical methods on it. Okay, that's just a recall of sets. So here we have our dictionary. Again, this is just a recall of dictionary. Yeah, so this is simply, so when you want to manipulate a dictionary, you can do things like this. Say my phone dict is, say Ben has phone number 888 and Raz has phone number 333. Then I can just assign my dictionary like this. And then I can ask, so if I say my phone dict of Susie, right, this is not in the original dictionary when I made it, it's 7, whatever this number. Then it'll simply create a new key called Susie. It'll find out Susie isn't there, so it'll create Susie as a key and add this value to it. So that's why when I call my phone dict now, it says Susie is 78987. So that's a basic behavior of Python dictionaries. In fact, this is what we will use to start going through a list of, I don't know, items we find online, and then we create some kind of a histogram or some kind of dictionary out of it. Okay, and here is the zipping. So my keys, let's say, is Ben, Raz, Susie. My values is 888, 333, so on. Now I can use my zip, right? It'll zip Ben with 888, Raz with 33, Susie with 78987. And then it'll take these tuples. This list of tuples can be passed in as argument to dict. And so nicely we can create a dictionary like that. So this is convenient.
So what happens if you have 2 equal keys? When you see.
So when we have 2 equal keys, I think the latter one will replace it. I don't know. Actually, let's try it.
Yeah, it will replace.
Yeah.
Okay.
Some. Yeah. So later on, I think when we do this dictionary thing, we will use dictionary, and we will first check if the key is there, and if it's there, we'll do something, and if it's not there, we'll do something. Okay, so here's a little bit of utries, just get your fingers dirty a little bit. So try adding to what we have, 2 more people. Say Fred is 1, 2, 3, 4, and Mary's phone number is 4 7s. So what will you do? Oops. Right. And okay, so now I should have Fred and Ben and Doris. Yeah, so it looks like it's putting things in alphabetical order, the keys. Some ordering. So now if we want to ask for Ben's phone number, we just do this. Okay. So then these are other methods. So I can put the dictionary's name and then ask dot keys in parentheses. So give me all the keys of the dictionary. And the same way I can ask and get all the values of the dictionary. So these values will be in the key order. And there is this other method called dot items, which will give me the tuples back. Okay? The key value pairs back. So these are all, I will assume you will know all about this from now on. It's just some syntax and yeah.
Dictionary is basically a list of tuples.
Yeah, so dictionary, yeah. So you can ask what are the items, and it just gives me a list of the tuples. That's basically what's in a dictionary, the contents of it. Okay. So now we have all the background to get into probability. Okay. Yeah, so the origins are at least 300 some years old, and a lot of it came out of very clever guys like Bernoulli and Pascal, and I don't know, trying to understand games of chance. So I don't know what this article is. Yeah, let's see. Yeah, there's a lot of philosophy as well. Like, we'll try to kind of keep it a bit pragmatic and not get too much into it, but I'll tell you the basics of the classical school, or the frequentist notion of probability, and then we'll also get a little bit into this Bayesian school, because it has some very useful ideas, but the axioms are the same for us, so we don't need to. Yeah, what happened to Kolmogorov? So Kolmogorov comes around in the something like 1930s, 20s, and then he axiomatizes probability. So we will basically start from there. Okay. So here are some main concepts. So what you want is this notion of an experiment, and that's really what's happening always under the hood. So an experiment is an activity or procedure that produces distinct or well-defined outcomes. Okay. So I don't know, if I flip a coin, that's an experiment, and I flip it again, same coin, right? And if in that case it has two outcomes, so the coin can come up heads, and it lands, and it can come up tails. Right? So this is my simple experiment E, coin flipping. Right? I can have an experiment that's much more complex. In fact, I was going to bring this today. So I have a measurable double pendulum that's hanging outside my office. So this double pendulum, yeah, I'll just explain it. Basically, it has optical encoders. So there are two arms, right? A single pendulum is like this, right? So it's fixed here, and then you pull it here and let go, and it does this, and do your physics experiments and find out the constant gravity and all this, writing down this ODE. So a double pendulum is more complex, right? So it has two arms, and this is not fixed like this anymore. So this is actually just, so there's another, think of this as so it can spin around, okay? And this can spin on top of this one. Right? So this is called a double pendulum. And then if you look into this, maybe I'll bring it next Friday, and maybe we'll do some experiments for fun. So it has these tiny little holes in it, okay? And an LED shines through it. There are 2048 holes in each arm, tiny holes, and then there is a photo detector on the other side, so it can keep track of which one of the 2048 positions each arm currently is. And time can be measured by some microcontroller code. It can be 1 millionth of a second if you want. So every 1 millionth of a second, it will try to keep its state, and it only keeps track of the states if they change. Okay. So all I'm getting is position x1, which is some angle for the first arm, and position x2. This is the angle for the second arm at some timestamp t. Okay. This is basically the raw data. That's also an experiment, right? So let's call that E2, double pendulum experiment. Both experiments, although this seems simple, I'll put links later on to. So there's this famous statistician at Stanford named Percy Diaconis. Actually, we should search this up. So he actually did this coin tossing experiment rigorously using some mechanical engineers in Stanford. Let's see, Diaconis. coin tossing experiment. Yeah, this is the paper. 40,000 coin tosses yield ambiguous evidence on dynamical bias. So I don't know if we can. So what they did is they actually constructed a coin tossing machine and they flipped the American quarter, same quarter. There's a lot of work into this, right? Yeah, here's the machine, right? So it's loaded on, there's a metallic ruler. They sort of affix the ruler on this inclined plane, and then there's an electromagnet and a switch. So the electromagnet, I don't know, does something, and then it releases it suddenly. And so this scale goes up, and then the coin flips and lands in this little bucket. So it's incredibly controlled experiment. They can repeat it, and then they count how many times, and they have some ODE model for this, and it's quite. So in the end, I think it's slightly biased toward being heads. So these are very interesting, and in both cases, these experiments are actually called chaotic. Right? Is Jordy's talk about chaos next week? Yeah. Okay. So that's something. Is that Thursday or Monday? Okay. So if you guys are bored, you can go to this talk. So they're called chaotic systems, chaotic nonlinear systems. Right? So, not the math guys, but does anyone know what is the definition of a chaotic system? Why are these two systems chaotic?
They aren't always the same.
Well,
The outcome.
okay, yeah, the outcomes are not. Oh, yeah, but that's good. That's good. There's something more elementary going on in this. So you see why they did this is like they can exactly put the amount of pressure that they put, the amount of tension on the scale and the exact placement of the coin, everything was highly controlled, right? And then if they go slightly off, okay, tiny bit off, up to even machine control, right? Electromagnet control. It'll come up heads or tails. So in the same with this one, I'll try to bring it next Friday. So we can clamp it to the board, and we can actually hook it to the laptop and see the measurements live, like where it is. So I can try to release it from almost exactly up to measurement precision. It will be exactly the same position x1 and x2 of the two arms. And if I release it, it'll go, and then boom. Maybe very soon it'll start taking a completely different trajectory. Okay, so in both systems, what's common is they're sensitive to initial conditions. They're highly sensitive to initial conditions. Right? And this is the physical model. Even the pure mathematical description of it, right? There's no noise, nothing. Complete mathematical description of the same process. Not identical, but something that captures the spirit of it is also sensitive to initial condition. That's the definition of a chaotic system. So two arbitrarily close initial conditions. I don't know. So in this case, it'll be x1 at time 0 and x2 at time 0. Say this is one initial condition, right? This is time 0. That's where I start. Let's say if this one is not equal, slightly off, 0, and then x1 of 0 is just slightly off by some tiny amount, epsilon, and x2 of 0 is slightly off by some amount, epsilon prime. If these two are not equal, and however tiny this is, essentially, can create the two trajectories to be completely divergent at one point. And if a system has this kind of behavior, it's said to be chaotic, right? So these are a couple examples of experiments. So for us, we don't have to really worry about whether things are chaotic or not. When we just say an experiment is just an activity or procedure that produces distinct or well-defined outcomes. Then the set of such outcomes is called the sample space. So these are all new definitions for you, right? So this notion of an experiment, kind of procedure you do, And then every time you do it, you produce a different outcome. But then the set of all possible outcomes are, I'm not going to write everything down, but just highlight the words. So there's experiment and outcome. And then this sample space is the set of outcomes. So every time you do an experiment, you get an outcome. The set of all outcomes is called the sample space. And it's often denoted by capital omega. Okay. So here are some roller die experiment. You know, sample spaces say, yeah, oh yeah, this is my favorite roll your die experiment, right? So the dice are painted with these colors, and then you can basically say my sample space is just these colors. Or you can have a flip a coin experiment where my sample space is just only heads or tails. Okay. And in this one, I draw a fruit from a fruit bowl. So I have a sort of well-mixed fruit bowl with 2 oranges, 3 apples, and 1 lemon. Then my sample space is, just draw 1 fruit out of the bowl after sort of twirling it around. Then it's just one of these 3 fruits, right? Orange or apple or lemon. Okay, so now is the next very, very important concept called an event. So an event is a subset of the sample space, right? So you want to think of the sample space as something floating around here, capital omega, with all these different possible outcomes. So a typical outcome could be little omega, right? So now an event could be some subset, right? So let's say it's an event A, is some subset of the sample space. Yeah, so for example, our event could be a citrus fruit, right? So that's well defined, subset of the sample space. That's the draw of the fruit experiment. So once we have these words under our belt, we can now define probability formally. So probability essentially is nothing but a map, a function. It basically it goes from a set of events to numbers in 0, 1. So to real numbers in the unit interval, that's its domain and range, right? So here is an event. This could be another event B, this is another event, and so on. So it unrolls omega into a set of events. So here's my set of events. And then my probability P is just a function that assigns to each element, each event, some value in the unit interval 0, 1. Okay, but it's not just any old function, right? That function has to satisfy some conditions. Okay, so here are the so-called axioms that it should satisfy. And this is maths, right? So we believe these axioms are self-evident. Right? But a lot of them actually make a lot of sense. The fourth one is the more difficult one to stomach, but it's useful. So for any event A, we say that the probability of A, right? So it takes A and it assigns probability of A. The first axiom says the probability of A should be some number between 0 and 1. That's the first axiom. So, okay, that's reasonable, or let's just suppose that's satisfied by the function. Then if the event is the sample space itself, right? So then it says the probability of the entire sample space should equal 1. This is the second axiom. Ouch. Okay. Sorry. You hate that too? Yeah. So then the third one is think about this. What is this saying, right? Before getting into details, what does this mean? Yeah, it's saying something happens, right? If these numbers, 0 means 0 and 1 are extremes, like 0 means, probability of something happening is 0, basically means it never happens. And if some event happening is 1, means it definitely happens. It means every time I do the experiment, it definitely happens. Then this is just saying that, it's just consistency, right? It's saying that my experiment is well defined. I have accounted for every possible outcome that can happen because my capital omega is the set of all outcomes. So when I do an experiment, something happens. We'll get into this a little bit more using limits soon. Then if I have two events, A and B are disjoint, that means, there's no little omega between them. So this is, say, my A, and let's say this is my B, this set. Say is my B, and A and B are disjoint, there's nothing common. Then the third axiom says, if A and B are disjoint, A intersection B is empty. This implies, that means if this, then the probability of A union B is equal to probability of A plus probability of B. So if the two events have nothing in common, then the probability of the union of the two events is simply the sum of the individual probabilities. Okay, again, that's an axiom. So we say our probability function satisfies these three. The fourth one is just basically 3, but kind of done in an infinite way. So suppose we have an infinite sequence of disjoint events, A1, A2, A3, and so on, right? Not just 2. Then we know that the intersection of any pair of them is empty by definition, so none of them intersect. Then what we want to believe is the probability of now we have something called a countably infinite union, right? So I take all these AIs and keep unioning them and getting this super thingy. So that set is well defined, or we know what it is. Then what this axiom says is the probability of the union of all these non-intersecting things is simply the sum of individual probabilities. It's basically the infinite version, countably infinite version of this one.
And,
yeah.
And that does not follow from 3, or?
No. Well, no.
No.
Well, that's, yeah. It doesn't follow from 3. Yeah. Well, yeah.
Shouldn't we just be dividing and combining the sets in a pairwise manner and get 3 from 4 or 4 from 3?
Well, see, remember, like 3, if I have a finite state space, think about it this way. If my capital omega is finite, then do I need 4? So I have like 8,000 billion possibilities, little omegas, but it's finite. Then I don't need 4 really, right? I only need 4 when I have something more going on, right? When my outcome space has, say, uncountably infinitely many events, and then I need some dense construction. Like if you want to play with reals, if your sample space is reals, and measuring the height of people or something, then your sample space naturally is reals. Then, yeah, I mean, that's somehow fundamentally different than discretizing all the people's heights by, 1 feet, or say by millimeters. Okay, this is a bad example. It'll matter for the double pendulum experiment. Right? The double pendulum experiment is really happening on continuous space, because the angle positions are 360 degrees. There, you really want the sample space to be continuous, for example. So the fourth axiom is generally explicitly said to be a separate axiom because it has this countable additivity thrown in. I mean, it's we just. So what is the motivation? Like, how did Kolmogorov, like, a lot of people are doing this intuitively way before Kolmogorov, but he axiomatized this. And the justifications are actually very simple. So this is the way you think about it. So it's called the frequency interpretation of probability, right? So the idea is that, say, we repeat an experiment a very large number of times, right? So then the fraction of times that the event A occurs will be close to probability of A. That's the motivation, right? And later on, we can understand the same motivations from a Bayesian point of view too, but let's just do the classical stuff. So here, what we mean is, so let capital N of A, comma N, be the number of times A occurs. So let it be the number of times A occurs when after you repeat the experiment lowercase n many times, right? Let's remember all this. So this is the most basic thing. So so number of times the event A occurs. So remember again, we have some thing and A is some specific subset here. And then I divide this by n, the total number of trials. Okay. Okay, sorry. This is A and n of A, and then what I want is so the intuition is that we want to understand probability of A as this limit, right? So it's the limit as n approaches infinity of this number n A comma n divided by n. So if A is heads, you know, and if it's a fair coin, then we would expect P of A to be half, right? So out of my, I don't know, 1 million times, roughly 500,000 of them will be heads, right? So when I'm going to divide 500,000 by 1 million, I'll get 1/2. So the idea is that this is a deterministic limit. It's just the classical notion of a limit. Yeah, so this is basically what we want. So we have n of A1 over 1, n of A2 over 2, n of A3 over 3. Question is, where is this fraction going? So when we look at this motivation for PFA and look at the three axioms, then this is what it means. For any event A, the probability of A being between 0 and 1 is simply this, right? It just says that the relative frequency of times A happens is always going to be between 0 and 1. That's just by definition. This numerator is between 0 and n. Then once again, if capital omega is the sample space, then immediately P of omega is 1. This is simply this statement in English. Something must happen because n of capital omega, n of the sample space n, is always n. Right? Something happens every time. So this one, if A and B are disjoint, so we know that there's nothing in common, then the number of times A union B occurs out of n times is just number of times A occurs plus the number of times B occurs because they're disjoint. So again, the addition operation goes through this relative frequency argument of two sets that don't intersect. Okay. So all of this is no magic. It's just justifying this notion. It's trying to make that notion sensible. Yeah. So I said axiom 4 is sort of more controversial, but only in certain circles of constructive math, so we don't worry about it. The proof is in the pudding. It helps. A lot of financial engineering uses this assumption. Pretty much everything we do probably uses this. So it's very, very useful to have around. Okay, here is tossing a fair coin example. So formally, our sample space is, say, head and tail, and my probability of head, this probability of tail is half. I can simply, now I'm giving you a model, right? Model for a fair coin toss. So what do I have to do in a model? I have to just give you the sample space, which is the collection of all possible outcomes, and then I have to give you probabilities for each of these outcomes. So, and I've given that, so we can represent a probability as the following function. But remember, probability itself is a function that goes from the entire sample space, right? So you guys see that if omega is head and tail, what is the set of all possible events for omega? Set of events. So here's my set of events. So it has the whole sample space in it, right? Head and tail. It has head in it by itself, tail in it by itself, and it also has the empty set, right? Yeah, so, oh, this is really bad. Oh, no, it's not, it's fine. Sorry. So then it's just, so the probability is simply a mapping that goes from this domain to some values in the unit interval, right? And in this case, the specific values are, this goes to 1, head and tail go to half, and the other one goes to 0. So that's all that is, and I'm explicitly telling you what the actual values are for a fair coin toss. Right? So yeah, and this is all like, I don't know, so normally in textbooks you only see P of H, they won't put the set around H, but that's because they're just convenience, notational convenience, you drop it, but actually there is a, yeah, H by itself is, yeah, it's actually like this. Okay, so now we can again check that our axioms are satisfied, right? P of H equals P of T is half, it's definitely between 0 and 1, probability of the entire sample space is 1, or we just said so. And then the, yeah, this is satisfied, the probability of the whole sample space is 1. And then, you know, because H and T are disjoint, the probability of that set, the only set that has more than two or more elements is just the sum of the individual probabilities. So all our axioms are satisfied. So then our next example is tossing an unfair coin, right? So it's just that now maybe the head is more likely 3/4 of the time, the tail is 1/4 of the time. So this is exactly the same, right? We just have to make sure that probability of omega is still 3/4 plus 1/4, which is 1. And clearly, first axiom is satisfied because these are just numbers between 0 and 1. Okay, and additivity is also fine. So, you know, this already gives you the elements. So now I can immediately introduce a variable called theta for the probability of heads, right? And so now I already have an inference problem. So we'll probably, I'm not sure if we'll get to inference today, but next week we'll all be mostly inference. So you see, if I have theta to be my probability of coming up heads, right? And clearly that already tells me 1 minus theta will be the probability of coming up tails, right? So theta is an unknown, let's say, because in the first example it was fixed at half because we said it's a fair coin. The second example we said it's an unfair coin, but theta is exactly 3/4. But theta, where will theta lie? You think of it as all possible values theta can take. So it can take any number between 0 and 1, right? It's the bias of a coin, right? How often will it come heads? So, you know, so what we will pretty soon start doing is defining a random variable called a Bernoulli random variable. So this is actually Bernoulli So it has a parameter theta, and theta can be any number between 0 and 1. But for a fixed value of theta, we now have a model for a theta-biased experiment, right? That means so normally head is encoded as 1, and tail is encoded as 0. So once we start encoding outcomes as numbers, real numbers, then we already have real valued random variables. Because instead of symbols, now we can have outcomes that are real valued. So that's just where we're about to go. So here's a little example 3. This is a New Zealand Lotto. And so here in New Zealand Lotto, there are 40 balls. I mean, and the balls are numbered 1 through 40. And it goes through this big machine, and out pops various balls. So I'm sort of only looking at the first ball that popped out of this New Zealand Lotto machine for a few decades. So and it's a well-stirred urn, right? There's a whole industry that does the machinery to inject air and whatever, well distributed, right? It's a big business. So you would expect that the ball label that pops out has equal chance because there are 40 labels. So a natural model will be the probability of little omega, where little omega is one of these 40. Tuple. Yeah, so the model is that little omega could be one of these 40 numbers. I'm going to say each one has probability 1 over 40. Right, that's all I'm doing here. So probability of label 1 equals probability of ball label 2. All of them is 1 over 40. So this is just a generalization of a fair coin to a fair lotto ball. And so suppose my event is this. I'm interested in what is the probability of the first ball being even, right? So that's my event. Ball labels are 2, 4, 6, 38, 42. And so to compute the probability of that, because I know that these don't intersect, they're distinct, right? I can apply this axiom 2 or 3 again and again. This is what you were thinking of, but this will, this will apply.
You can only get finite units.
Yeah.
Using property 3.
Yeah.
You will never get the infinite.
Yeah.
What does it start from property 4?
Well, then it's fine.
Yeah, property 4 implies property 3.
Yeah.
But for property 4 to be consistent, you need higher conditions on your sample space. So property 4 requires something called a sigma algebra set, whereas property 3 only requires an algebra set.
We define sigma algebra soon. We'll see it. But it's just, it's a different beast. It's another layer. Do you want women to have the right to vote or not? It's kind of a new thing. I mean, that's me, you know what I mean? I don't know, it's a new thing, it's a new level of axiom. It's very different. It doesn't follow from 3. And like Dan says, it imposes restrictions on what these functions are and how you can close them downstairs.
But it's correct then to say that we need either 3 or 4, depending on if it's a finite situation or an infinite situation. So
yeah,
we don't need 3 and 4, we need 4.
Yeah. So I mean, you can do a lot with 3, but I think 4 implies 3. But it's just once you get the feel for it and actually look at problems, you'll see why it's a lot more to believe. And it actually comes in what he calls this formal thing called sigma algebra. Your set of events have to satisfy some conditions that actually make axiom 4 hold. So I think I defined all of this downstairs. So let's continue. I want to get a little bit further before. Yeah, sorry. I'm like I kind of grew up in upstate New York, so I have weird jokes like women right to vote. What I meant is, it's an axiom, right? Because Seneca Falls is where the women's liberation movement happened. It's just very close to Ithaca, where I went to school. So there they write this in the waterfalls. We believe these truths to be self-evident. All men and women are created equal. I mean, that happened in the late 1800s or something. That's what I mean. I don't know. Blacks, of course, or considered men, right, in the US. So it's like it's a new axiom. All right, so all I'm doing is just breaking it down because it's finite. I can keep iteratively applying this pairwise property, and it terminates. So that's all I'm doing there. And this just amounts to multiplying it by 20, and the same thing for oddballs, right? It's just a little calculation. Okay, so the set of all possible subsets of omega is called the power set, and it's denoted by 2 to the omega. So often this is a convenient place to work if omega is finite, right? If this set is finite, less than some number, I mean some finite number, then I can consider all possible subsets of omega. And if my probabilities are assigned to every atom, every little omega, every outcome, then I can definitely use that assignment to define the probability of any subset, right? Because I just enumerate through all the little omegas in that set, and then I can say, I just add them all up, and I'm done, right? So this is nice, but you don't need to work with power sets all the time. So you can also have this so-called trivial algebra. So you can take, so this is this power set is one possible set of events. So events could be this power set, right? And this is when the size, so when you put an absolute value, it means the size or cardinality of omega. When this is finite, you can do this. But another set of events is, so the set of events. Another one is this one. So you can take all of the sample space, like something happens, and then you can have the empty set. Nothing happens. This is very boring on the other end, right? So all you can ever say is something happens. If you do the experiment, right? And nothing can't happen. So that's the other extreme, and this is also fine. This is all you need. So you map 1 to this, 0 to this, and you're done. All the axioms are satisfied. And this is the richer one. So, man, should we go through the property? Should we take a fika break? Yeah, we'll come back to the properties, maybe fika break. Oh, this is good. We probably will be done with probabilities and random variables before end of today. Which could be good. So, yeah, I always think I don't have enough content, and there's always more than I can handle, which is good. Yeah, so it'll be good if we can get to these 2 notebooks today. And so is the pace a little bit better, more interesting now, or it's going to get faster? Don't worry. Okay, so let's have some fika.